This is exercise 6.5, motion of a particle in a straight line. When we look at the motion of a particle in a straight line, we'll be looking at three different things. We'll be looking at displacement, we'll be looking at velocity and acceleration. So we'll be looking at three quantities. Displacement. So displacement is x, and it measures the distance of a particle from a fixed point, known as the origin. Okay, displacement. So displacement, that's the first quantity we'll look at. It measures the distance of a particle from a fixed point, or the origin. So for example, if this is the origin here, if the particle comes along here, then on this side displacement would be positive. To the left and to the right of the origin, here displacement is negative. So to the right of the origin, displacement is positive. And to the left of the origin, displacement is negative. Okay, so displacement can be positive or negative. This is the origin here. Okay? Yeah, is at the origin. The displacement is 0. Is 0. That means that x is 0 there. Velocity is a measure or measures the rate of change of displacement with respect to time. So in other words, velocity is dx dt. Okay? So therefore, the velocity is just the gradient. So velocity will be the gradient of the displacement versus time graph. The reason is, you know, dx dt is the first derivative of the displacement. So velocity is just the gradient or the first derivative of the displacement versus time graph. So if I give you a displacement versus time graph, the gradient will be the velocity at that particular time. Okay, because the gradient is the change in, for example, if I look at a graph here, so let's say I've got x versus t, and let's just say it's a straight line, okay, isn't the gradient of this graph will be the rate of change of x with respect to t. Okay, so if I want to find the velocity of this particular point, I just need rise over run. So the gradient here is rise over run, but it also will give me the velocity. For example, I may move, I don't know, 20 meters in 5 seconds. Okay, so actually, what have I done wrong there, girls? Time x. Thank you. X versus t. Because when I was doing my rise, I was getting time. It's displacement over time. Isn't speed distance over time? Yeah. Okay, so that's x versus t, always the independent variable on the horizontal axis. So time and displacement there. So the gradient, which is rise over run, will be the velocity. Okay, because it will be the change in the displacement over the change in time. So it actually is the formula for average speed. Okay. Now with a graph like this, your velocity is constant because your gradient is the same. So this has a constant velocity, this graph. Does this make sense or not? Constant velocity, because if you worked out the gradient, so this graph here has constant velocity, because if you work out the gradient at any point on the graph, you'd get the same answer, okay? Because for every so many seconds, for example, or so many minutes, whatever, you've got the same change in displacement. So this is a constant velocity graph. But if you look at this graph here, this is not constant velocity. So with this graph here, the gradient, the velocity, you can't actually work out the gradient at any point on this graph. With the second graph, how do you work out the gradient? Or the speed at any point, or the velocity? Gradient of tangent to curve. So with this graph, so for this graph, velocity is not constant. So the velocity is not constant. And so therefore the velocity equals the gradient of the tangent to the curve at any point, at that particular point. So velocity at a particular time is the gradient of the tangent to the curve, okay? So in other words, tell me where you think, see, look at the gradient here and look at the gradient there. So I'm going to call that gradient 2 and gradient 1. Looking at that graph, where do you think the gradient is higher or bigger? Bigger gradient. Gradient 2, it's going faster. Gradient 1 is not as steep. So the particle is travelling faster, motion is faster at position 2 than it is at position 1. So this would be speeding up. Now, we're also going to look at concavity here as well. All right? So you know how this will all work for, so we've got x versus t. When we've got x versus t and you look at the gradient, you're looking at velocity because velocity is the first derivative. Okay, so you've got displacement, then you've got velocity, then you've got acceleration. So to find velocity, it's the first derivative, okay, dx dt. So here we can say that the velocity at, I'm just going to call it t2, and maybe down here is t1. So the velocity at time 2, at t2, is greater than the velocity at t1. We can see because the gradient is steeper, because the gradient's bigger, because the gradient at t2 is greater than gradient at t1. Okay? All right. We'll talk about acceleration a bit later. Up here, velocity can also be written as x dot. So we can also write that x dot equals dx dt. Okay, so velocity is dx dt. This can also be written as x dot is dx dt. What do you think acceleration is going to be? X with how many dots? 2 dots on top. Okay, we'll do that in a minute. Now, speed, we never talk about negative speeds. You can never travel at negative speed, but you can have negative velocity. Velocity, unlike speed, has magnitude, size, and direction. Okay? Now, displacement, what is like what? You know, displacement has size and direction, but what doesn't? Distance travelled is always positive. So distance travelled is always positive, but displacement can be positive or negative. So if I say, for example, my displacement is -2, it means I'm left of the origin by 2 meters or whatever units. If my displacement's +5, I'm 5 meters to the right of the origin. Whereas distance travelled, for example, is always positive. You never have a negative distance travelled, but displacement, if I say my displacement's -5, it means that I'm 5 units to the left of the origin. Now, velocity, unlike speed, has magnitude and direction. So it can be positive or negative. And so can be positive or negative. So if velocity is positive, you are travelling which way? In the forward direction. So if velocity is positive, for example, positive 60 kilometres per hour, you are travelling, or motion is, I'll just put you are travelling in the positive direction, which is often to the right, in the positive direction, which could mean to the right of the origin. Actually, wait a sec, you don't have to be on the right of the origin, you just have to head in the positive direction. So you're travelling in the positive direction, which is to the right. So don't put to the right of the origin, it's just to the right. You can still be travelling to the right. So let's say the origin's here and I'm travelling here, that way, that's positive velocity. Positive velocity, if you're travelling that way, to the right. So I could be travelling to the right down there or here. As long as I'm travelling to the right, I've got positive velocity. But once I turn around and travel to the left, the other way, I've got negative velocity. Okay, so got that. One sec. So if velocity is negative, it means, for example, negative 60 kilometres per hour. That means you are travelling at a speed of 60 kilometres per hour, heading, you're travelling at a speed of 60 kilometres per hour, but you are towards the left or going left. Does that make sense? You are travelling in the negative direction. So if velocity is negative, so for example, negative 60 kilometres per hour doesn't mean you're travelling at negative speeds. No one can do that. We're not time travellers. We don't go back in time. So we've got 0, there's the origin. It doesn't matter whether you're travelling down here or up there. This is negative velocity, because you're travelling in the negative direction. Okay? What about if velocity is 0? It means that you are not moving. And you don't have to be at the origin to not move. So if velocity is 0, you are stationary, or the particle is stationary. Let's go. The particle is stationary, it's not moving. The particle is stationary. In other words, it's not moving. And we write v equals 0, or dx dt is 0, or x dot is 0. Now, at rest, or it's at rest. That's another way that they can say it. 8 times that you would be at rest. Let's say you're travelling in the positive direction, and then you have to stop to turn around, unless you go like that. But this is particles moving in a straight line. This is particles moving in a straight line. So you have to, if you're travelling in the positive direction, you have to then stop and come to rest, and then you'll travel back in the negative direction. So it's like just thinking of a number line. I think we've spoken about this before with second derivatives. You know how you go second derivative is negative and then it becomes positive? Well, you've got to, when you go from negative numbers to positive numbers, you have to pass through 0. So when you've got, say, a positive velocity, let's say this is my scale for velocity, and these are positive numbers, 1, 2, 3. Well, you've got to come through to 0 to get to negative 1, 2, and 3. Does that make sense? So velocity is also sort of on a scale. So if you're travelling in the positive direction and you stop, and then you travel in the negative direction, you have to stop first and come to rest. So this is motion of a particle in a straight line, not going around a circle. That's why we know we come to rest when we turn around, okay? Anyone? Acceleration is a measure of what? Acceleration, yeah. Acceleration is a measure. So acceleration is a measure of the what? Rate of change of velocity. Yeah, little a. Is a measure of the rate of change of velocity with respect to time. Girls, it's really important that you put with respect to time, because in the extension part of the course, you'll be looking at velocity and acceleration, but not in terms of t, in terms of x. So it's really important for the 2-unit course that velocity is dx dt and acceleration is dv dt. Okay, so therefore acceleration is dv dt. Now we know that v is dx dt, which is y, so a is dv dt. Now I'm replacing this v with dx dt, so therefore can you see that you've got d squared and d squared t? So therefore it's d squared x by dt squared.
Where did you get the d over dt?
Okay, the dv dt.
No, the d.
Oh, this?
The other part.
This?
Yeah.
Oh, because I've written d by dt and I've replaced v, we know is dx dt. So I've kept the d by dt. So it's d by dt of v. So v is replaced with dx dt. So therefore, we know that to get acceleration, you have to differentiate twice, and that's how you write the second derivative, d squared x by dt squared. No? So therefore, wait a sec, acceleration can also be written as x double dot. Now, again, acceleration can be positive or negative. On which direction it is acting or it is in. So, if acceleration is to the right, now we need to talk about how objects speed up and slow down. Okay, so if acceleration is to the right, it doesn't mean the particle's speeding up. It just means that acceleration is positive. So if acceleration is to the right, acceleration is positive. And if acceleration is acting to the left, so if acceleration is to the left, we say that the acceleration is negative. And you can also have zero acceleration. In other words, if you're not accelerating, doesn't mean you're not moving. It just means that you're not changing speed. So, I'm going to draw these in a minute. And if acceleration is 0, the speed is not changing. Girls, I can put my car into cruise control. So I can be travelling on the highway at 100 kilometres an hour. I'm not accelerating. I'm travelling at the same speed. So when you're travelling at the same speed, you are not accelerating. Okay, when you're accelerating, as you know it, you're speeding up. That's acceleration. Doesn't mean it's, well, you know, when you think of a car and you put your foot on the pedal, you're accelerating. When you put your foot on the brake, we're decelerating. But we're going to look at that as accelerating sort of in the negative. Well, it depends if it's acting in the same direction as the velocity or not. I'm going to talk about that in a minute. Okay? So if acceleration is 0, the speed is constant or not changing. That does not mean that you are not travelling at all. So you could have acceleration 0 and speed 0, meaning you're stationary. But you could have acceleration 0, speed 60, meaning you're travelling at a constant speed of 60. Okay? So if acceleration is 0, the speed is constant, not changing, it does not mean that the speed is 0. And the other thing is, as well, is when you go from negative acceleration to positive acceleration or vice versa, you must pass through 0 acceleration at some stage. So the other important thing is, when going from negative acceleration to positive acceleration, you must pass through 0 acceleration. Because just think of it on a scale. So for example, if this is acceleration and you've got positive numbers and negative numbers, 0 is in between. Okay? Where did I put speed? It does not mean that the speed or velocity is okay. Yeah, speed or velocity in this. Because velocities just give me the direction of the speed, okay, whether I'm travelling. So velocity is speed, but the velocity tells you, am I travelling to the left, am I travelling to the right? That's all velocity tells you. Gives you the speed plus your direction, okay? Now, I'm just going to draw some diagrams here. Accelerating to the left, it's negative acceleration. If you're accelerating to the right, if that's the direction, it's positive acceleration. And if the speed's not changing, there's no acceleration. Now, it does not always mean, if there's acceleration to the left, it doesn't mean that you're speeding up. It doesn't always mean that, okay? So this is what we're going to do. You are travelling to the right. Velocity is positive, right? Travelling to the right. Velocity is positive. And acceleration is to the right. Acceleration is positive as well. Then would you speed up or slow down? So let's say you're travelling that way and you're accelerating that way. Let's say someone's pushing you. You will speed up, okay? So if acceleration is in the same direction as the velocity, then the particle speeds up, which you call accelerating. So just think, if you're travelling that way and someone's pushing you, not in a shopping cart, just in something else. Just think of something that you can be pushed in, like a bike. You know, a kid on a bike, a child. And they're travelling that way and you push them. Then they're going to speed up because you're pushing in the same direction as the velocity. But let's say you want to stop that. Let's say the kid's going too fast and you need to stop them. You would often get in front of them and stop them that way. Do you know what I mean? And that would be, so if acceleration is in the same direction as velocity, then the particle speeds up. Wait, that's right. I was about to do that. So we've got that scenario, or velocity here is negative, acceleration is negative. So if the velocity is this way and the acceleration is that way, yes, the particle is accelerating, but this particle here, so if acceleration is in the same direction as velocity, then the particle speeds up. So this particle is speeding up, travelling which way? Speeding up, travelling to the right. Travelling to the right. So for this one, for example, velocity is negative. The velocity could be negative 60 kilometres an hour and it's accelerating, so it's speeding up and it's going to go 80 kilometres an hour towards the left. This particle is also speeding up, but it's travelling to the left. So girls, negative acceleration does not mean that it's slowing down. You have to look at it in conjunction with the velocity. Scenario is if acceleration is in the opposite direction to the velocity, then the particle will be slowing down, or what you call decelerating. So for example, if the velocity is positive, this way, positive velocity, but acceleration is this way, negative acceleration, then the acceleration is opposing. You're not giving it a push, you're stopping it. You're opposing the velocity. So this, therefore, it's traveling, this particle is traveling to which way, the right or the left? It depends. No, it's traveling. No, yeah. Just look, just at the moment, the way it is, let's say it's going pretty fast and we're applying this force. I'm not saying that we're going to stop it and then keep pushing it. If we stop it and keep pushing, then the velocity will change direction. But if we've just got this scenario where the velocity is that way and the acceleration's that way, that particle will be traveling to the right but slowing down. Now, if you apply enough acceleration to the left, it will stop and turn around the other way and go the other way. Okay, so our other option is if the velocity, if we've got negative velocity, so the other thing is if we've got negative velocity and we've got positive acceleration, then which way is the particle traveling? So in this case, the velocity tells you where the particle is traveling. This particle is traveling to the right but slowing down because the acceleration, you're stopping it, opposing the motion. With this one, the particle's traveling to the left, negative velocity, but positive acceleration, doesn't mean it's speeding up. This particle is traveling to the left, but is it speeding up or slowing down? Slowing down, it's decelerating. In other words, it's decelerating to the left. This one's also decelerating, not accelerating. Okay? So, negative acceleration does not mean traveling to the right. You have to look at it in conjunction with velocity. Okay, negative acceleration could mean that it's speeding up. If the velocity is to the left and acceleration is to the left, it's speeding up to the left. So this particle is traveling to the left but slowing down. Okay? Is if the particle is traveling at a constant velocity, for example, if we're traveling at a constant speed of say 60 kilometers per hour, it's constant, then the acceleration is 0. If this is traveling at negative 60 kilometers an hour, it doesn't mean negative speed, it just means it's traveling to the left at a constant speed of 60 kilometers per hour. In this case, if it was constant, then acceleration would be 0. If the velocity is not changing, if the velocity is constant and it's not changing, it's not speeding up or slowing down, then acceleration is 0. So it's example 6.5. So the graph below shows the displacement of a particle. So this is x versus time. Girls, you can see when is the particle at rest. What does at rest mean? X is 0, V is 0, or A is 0? X, yes. No, at rest means V is 0. Rest. Rest means not moving, meaning velocity is 0. So, girls, this is x versus time. Now, we know that v is dx dt. It's the first derivative. What am I looking for on that graph? Stationary points. Gradient 0. So, velocity is 0. Velocity is dx dt, or the gradient of the curve. So, where is the gradient of the curve 0? At the stationary points. So, therefore, it's at T3 and T5. Girls, it's all down here in your examples. Just one sec. When the particle is at rest, velocity is 0, dx dt is 0. So the particle is at rest at the stationary points T3 and T5. The next one, when is the particle at the origin? Origin's displacement. In other words, when does x equal 0? That's at T2, T4 and T6. So the particle is at the origin when x is 0, so it's on the t-axis. So that's at T2, T4, T6. And the last one says, when is the particle at its greatest velocity? So when is it now? You might say, what they want here is greatest velocity. Positive 60 is different to negative 60. So I want the positive direction, positive velocity to be the greatest. So if you had to choose between positive 60 and negative 60, you'd choose positive 60 because it's the greatest velocity. They're not asking for the greatest speed. Okay, so when is the particle moving at its greatest velocity? So,
in that case, the speed will be the same.
Is at its steepest. So when is the curve at its steepest? Because it's got to do with, so we know that velocity is dx dt, yes or no? So the greatest velocity will be when the curve is steepest. But we've got here either there or there. Actually, the particle's moving back in the negative direction.
So you're looking at the inflection?
Yes, I'm looking at the inflection. So the inflection will be when it's, you know how we go positive velocity, positive gradient, smaller positive, 0, negative gradient, biggest negative gradient. You know how we do that? Negative but not as big, and then we go positive gradients again. So the steepest bit is there. That's the steepest part of the graph. But if the particle's moving, this is x is plus, like let's say x here is +5, it's coming down. The particle's actually moving to the left there. So, what have they got? They've got it, graph is steepest at T4, but I'm just telling you here that it is travelling in the negative direction. How can you tell? Because if you look at time 3, you're further away from the origin. X is displacement for the origin, but if you look towards time 4, you're now back at the origin, so you're moving from the right. This is actually moving from right to left. We need to discuss this more tomorrow.
So what's happening?